Hey guys, welcome back to a new video. In this session we'll be solving 3 exercises on pulleys, which are an application of Newton's third law. But let's face it, they can be quite counterintuitive. That's why in the first 2 exercises we'll be building some intuition about the fundamentals of how pulleys work. And in the third exercise we'll actually be doing some involved calculations. But as always, we will do them step by step. And in the end we'll get a very satisfactory result. If you enjoy these videos, consider giving them a thumbs up and leaving a comment down below. Let's get into the first exercise. In the first problem, we consider the following scenario. Let's say that we have 2 weights connected to each other through a rope, and this rope passes 2 pulleys, as you can see on the sketch right here. And the simple question that we are going to ask in this exercise is the following. If we pull this weight backwards by 1 meter, by how much will this weight be lifted? And you might already quite easily know the answer by some trick that you've learned. However, it can still be quite useful to really think this exercise through step by step to get a systematic way of finding the answer. And to build up this systematic way, let's first look at a much more simpler scenario. Namely, the scenario where these 2 weights are connected by a same kind of rope, however now only by 1 pulley. In this case, it's quite straightforward that if we move this weight backwards 1 meter, that then evidently, because the rope has to remain the same length, that this weight is lifted by exactly 1 meter. And this is of course very straightforward, but how can we look at this situation from another angle? Well, first we realize that pulling this upper weight 1 meter backwards is equivalent to cutting a piece of rope with length exactly 1 meter away in this upper section. So therefore we have 1 meter of rope missing right here. Now since we assume that the rope does not change its length, we need to fill in this piece of rope again. So where will we get this piece of rope? Well, we look at the second section right here. So from this section we again cut a piece of rope of the same length, 1 meter. We remove it from this section and we paste it again right here in this first section. However, at this point we see that we need to connect these 2 pieces of rope again, because in the end, by pulling this weight backward, the rope did not change its length. And since this piece of rope that we cut out is exactly 1 meter, this means that this weight needs to be lifted by 1 meter to piece these 2 pieces of rope together again. And this is a roundabout, however systematic way of saying that this weight has to also move upward 1 meter. So let us now use this systematic approach in the scenario that we initially had with the 2 pulleys to see by how much this weight gets lifted if we move this upper weight 1 meter backwards. Again, pulling the upper weight 1 meter backwards is equivalent to cutting out exactly 1 piece of rope of length 1 meter out of this upper section right here. So we remove a piece of rope right here, which is equivalent to moving this weight 1 meter backward. Now we want to replace this piece of rope that we cut out by another piece of rope from the second section. Therefore, we cut out a piece of rope again from length 1 meter from this section and we paste it again in this upper section. So we basically moved the missing piece of rope from this horizontal section to the vertical section. And now we've come at the point where we could say that we can connect these 2 pieces of rope again and from this derive how much this weight lifts. However, in this case, that would not immediately translate to how much this weight actually has to be lifted. Because we see that if we pull on this piece of rope and we connect it again to the upper piece, that a large part of the rope actually goes over this pulley. And therefore it does not fully correspond to the distance that this weight has to be lifted. So we have to do one more step. We see that this hanging weight is actually supported by 2 ropes, one on the left and one on the right. Therefore, it makes sense to take this piece of missing rope on the left side, divide it by 2, and take 1 missing piece of the right hand side. Therefore, we cut again this piece of rope on the right hand side and we paste it here on the left hand side. And then at this point, we see that by connecting these 4 pieces of rope together, these 2 pieces together and these 2 pieces together, that we have to lift the weight exactly this distance. However, what is this distance? Well, this is exactly the entire distance that we had before, L, however now divided by 2, because we've split the distance of this missing piece of rope exactly in half. And therefore we see that if we pull this weight right here 1 meter backwards, that the hanging weight will be lifted exactly 1/2 the distance. And this of course also works vice versa. If we want to lift this weight by exactly 1 meter, let's say, then we now know that we have to move this weight 2 meters to the back. And so we see that these two distances are connected by a factor of 2. And this of course has to do with the fact that we exactly have 2 pulleys right here. And then, as you might already know, this can be generalized to more pulleys. If we, for example, have 4 pulleys, which is a much more complex system, then that would mean that the conversion factor would be 4x. And of course, we see that for 1 pulley in this scenario, the conversion factor is simply 1. In the second exercise, we are going to be looking at the properties that pulleys are invented for, lifting heavy weights. And more specifically, the property that you can lift heavy weights by exerting a much smaller force. And to do this, we will again compare 2 scenarios, one simple one and one advanced. In the simple scenario, we have a weight of 10 kilograms attached to a rope, and this rope goes through 1 pulley. Now, of course, we know that since we are on Earth, there is no escaping gravity, and the gravitational force pulls on this weight downwards with a force of approximately 100 Newton. And we know now from Newton's third law that this actionary force requires a corresponding reactionary force. And this force will of course be the tension in the rope. And since this weight is not moving up or down, we know that the tension in the rope will also be 100 Newton. Now, since this rope is in equilibrium, meaning that it does not contract or dilate, it remains the same length, this means that this exact tension force will also be present on the other side of the rope, and this will also be 100 Newton. And to counterbalance this, this means that if you want to lift this weight upwards or simply keep it suspended where it is, you need to exert a force of exactly 100 Newton in order to keep this weight suspended. So in this case, the pulley did not really help at all. We still need to exert the force, which is equal to the force that is pulling the weight downwards. In the second scenario, we again have the same rope and the same weight of 10 kilograms. However, in this scenario, we have exactly 2 pulleys. And the rope is actually attached to one of the pulleys, namely the larger one. And now the question is, what is the actual force that you need to exert on this rope right here in order to again lift this weight? In the previous scenario, this was 100 Newton. However, what will it be in this scenario? Of course, it starts again with the force of gravity acting on this mass and pointing exactly downwards. And the magnitude of this force will be 100 Newton. And again, we can use Newton's third law that this force actually has to come with a reactionary force, which of course will be the tension in the rope. However, we see that the weight is actually carried in this case by 2 ropes instead of 1 rope in the previous example. Therefore, the entire reactionary force of 100 Newton will now be divided by 2, and the tension in each of these ropes will then of course be each 50 newtons, which will add up to 100 Newton to counterbalance the force of gravity. Let's now follow this side of the rope, which has a tension of 50 Newton in it, and follow it all the way down where we are actually holding the rope. Similar as in the previous case, this 50 Newton of tension is simply translated to the other end of the rope, so this will also be 50 Newton. And because the tension in the rope at this point is 50 Newton, we need to only exert 50 Newton to keep this weight suspended. And therefore, we see that we only need 50 newtons to support a weight of 10 kilograms, which is attracted towards the Earth with a force of 100 Newton. So thereby, this pulley of 2 systems made it so we only have to exert half the force in order to keep the same weight of falling. Now, comparing these 2 cases, does this mean that we actually have to exert less energy in the 2 pulley system compared to the 1 pulley system? Well, no, because in the previous exercise we exactly looked at the relation between the distance that we need to pull the rope in order to lift the weight in the one pulley system, if we want to lift the weight by exactly 1 meter, we saw that we have to pull the rope exactly 1 meter. However, in the two pulley system, we saw that if we want to lift the weight 1 meter, because we have two ropes right here, we need to pull this end of the rope exactly 2 meters, because there is a conversion factor of 2. And therefore, we see that there is a trade-off between the two. In this first case, we need to pull the rope much less distance, but we need to exert much more force over this distance. Whereas in the second case, we need to exert much less force, so it will be easier to pull the weight up. However, we need to exert this force over 2 meters instead of over 1 meter. And this brings us to the concept of energy, on which I will make many future videos. In the third and final exercise, we are going to be combining our knowledge of the inclined plane and our knowledge on pulleys and Newton's third law. In this scenario, we have an inclined plane with two masses connected to each other by a rope over a pulley. Now, in this exercise, we consider this inclined plane having no friction at all. And the actual incline of the inclined plane is defined by this angle alpha. And the question in this exercise is to find the acceleration of the object with mass m1 in the downward direction, and this as a function of this angle alpha, because we already have an intuition that if alpha becomes very small, then the inclined plane will be very steep and this downward acceleration will decrease. However valuable this intuition is, let's try and put it in a more mathematical form. The first step in such a Newtonian mechanics problem is always to identify the forces that are present in our system. And I've made a separate video specifically on this type of reasoning. So let's first look at the object with mass m1. For the first force, we acknowledge that there is no escaping gravity. Therefore, there will be a gravitational force pulling this weight downwards. And we denote it by Fg with a superscript 1. Since it's the force of gravity that is acting on object 1. This same force of gravity, of course, is also present on object 2. It will also be pointing directly downward, and this one we will call Fg2. And returning to object m1, we can use Newton's third law to identify a tension force that is opposite to the gravitational force. It's of course the tension force in the rope that is preventing this object from falling down. So this will be the tension force in the rope, which we denote as T. And since the rope does not change length and is in equilibrium, we know that at the other end of the rope, the same tension force will be present. So this will also be T. Since if these two forces would be different from each other in magnitude, then that would mean that there would be a net force inside of the rope. And then this net force would change the length of the rope. However, this is clearly not happening, so these two tension forces have to be the same. And there is one more force that we need to take into account here, which is of course the normal force, which is perpendicular to the surface of the inclined plane and prevents our object from falling right through. And this force we will call Fn, the normal force. And so at this point we have completed step 1, which was to identify the vector forces in our system. The second step is one that is also always needed in order to be able to perform any calculations, which is of course to define and draw our coordinate system, our x and our y axis. Now here there are two obvious choices. The first choice would be to take the y direction in the direction in which we want to know the acceleration of our block m1. So we would take this to be the y direction and then this to be the x direction. However, this choice makes it quite difficult to compute all of the forces of m2, because we have this normal force and this tension force that are both in the x and y direction. And this will give us some very difficult calculation with components and other stuff that we want to avoid. Therefore, we go to the second choice of coordinate system, which is the coordinate system that is oftentimes used in inclined plane exercises. And this is of course to take the x-axis along the inclined plane and the y-axis perpendicular to it. Now of course it's important to note here that at this point our acceleration that we want to find of our m1, which will be AD in the down direction, will not be exclusively in the y or x direction. Since it would be in this direction, we need to do some extra calculations later on. However, this will turn out to be the most convenient coordinate system. At this point, we have first identified our vector forces on our figure. Secondly, we have chosen a coordinate system and the orientation of its coordinate axis, and therefore it is time to dive into some calculations. However, before we do so, let's first briefly recap what we actually need to find in order to start these calculations. As you remember, the question in this exercise is to find the acceleration in the downwards direction of this block M1. This means that we need to find the acceleration in this downward direction. Now, since we have chosen our coordinate axis in this fashion, this acceleration will not be in either the x or the y direction. And therefore, we will call this acceleration AD, d for downwards direction. Now we know from Newton's second law that the acceleration is proportional to the net force that is acting on this object. In this case, it will be the net force between the downward force of gravity and the tension force that is pulling this weight upwards. And we know, due to the fact that the rope is in equilibrium, that this tension force will be determined by this tension force right here, and in turn this tension force will be determined by the other forces acting on the second object. And therefore what we need to do is to find the net force on this first object, and from this we can find the net force on the second object. It is also crucial to realize at this point that the motion of the object of which we want to find the acceleration in the up and down direction will be equal to the motion of this second object in the x direction. And this is of course due to the fact that both objects are connected with this tight rope. We start by applying Newton's second law on the second object, and we will do so in the x direction. We know that Newton's second law is that the net force, so the sum of all the forces in the x direction, will be equal to the mass of this object, in this case m2, multiplied with the acceleration in the x direction. Thus, we are left with determining the forces in the x direction. And to do this, we first start by drawing this parallel line to the inclined plane, and it will be also parallel to the x direction, to realize that this angle here of the force of gravity with the inclined plane will also be the same angle alpha. And from this we see that there are two forces that have at least one component in the x direction, namely the force of gravity and the tension force. The tension force, of course, is completely in the positive x direction, since it's parallel to the inclined plane and thus parallel to the x direction. We see that the force of gravity has a component in the negative x direction, because if we project this force onto the x-axis over this angle alpha, we see that it has a component in the negative x direction. Thus, using the basic principles of goniometry, we see that we have minus fg of object 2, the force of gravity pointing downwards, but we multiply this with the cosine of alpha in order to get the x component. And we know that this will be equal to the mass 2 multiplied by ax, the acceleration in the x direction. And we already have our first equation derived from using Newton's second law. So now that we've written the forces of the first object in terms of Newton's second law, we will look at the forces of the second object, the object that is suspended by the rope and of which we want to find the downward acceleration. And in this case, we will look at the forces in the y direction. So we have that the net force, or the sum of all the forces in the y direction, will be equal to the mass of the object, in this case m1, multiplied by the acceleration in the y direction. So now it's very important to note that this acceleration that we're looking for, AD, so the acceleration in the downward direction, is not directly equal to AY, the acceleration in the y direction. And to make this very clear, let me just redraw our object here with all of the forces that are acting on it, but without the inclined plane to avoid any clutter. So we have our object right here. We have, of course, the tension force that is acting in the upward direction. We have the force of gravity that is acting exactly opposite in the downwards direction, so Fg of object 1. And what I'm going to do now is to draw the coordinate system with the origin in the origin of this object, just to make it clear how the angles work. We know from our original sketch that the x and y axis were drawn like this, with the x-axis parallel to the inclined plane, which is at an angle alpha with the vertical direction. Thus, we can draw something like this. The x direction will be parallel to the inclined plane, and the y direction will be perpendicular to this x direction. So we have x and y. Having drawn the coordinate axis, we can also identify the angle alpha, just like this. And to make it more clear why this exactly is, let me just sketch the outline of the inclined plane. We had that this was an angle alpha, and therefore, because this side and this side are parallel to each other, that would mean that this will also be an angle alpha. And equivalently, also this angle will be the angle alpha. So let me just remove the inclined plane again, and we have two angles alpha. But here, of course, we want to extend the x-axis in the negative direction, and also for the y-axis, we want to extend it into the negative direction. And so at this point, we have all the angles and the axes that we need in order to fill in this equation in the y direction. And let me just remind you that this equation holds in this y direction. Therefore, we fill in all of these forces, which are now the y components of the forces that we're dealing with. We see that the y component of the tension is in the positive y direction. So we have Ty as the first force in the y direction. We see, of course, that the y component of the gravity force is in the negative y direction. Therefore, we have minus f of g1, but now in the y direction, so a second subscript. And this, of course, will be equal to m1 multiplied by ay. And let's now take a moment to connect this ay, the acceleration in the y direction, with the acceleration that we actually want, which is, of course, ad. And to do this, let's first make a note on the sign of the magnitude of ad, the acceleration in the downwards direction. If the object is moving downwards, then the sign is plus, so then we have plus ad. If the object is moving in the upward direction, then we say that ad has a minus sign in front of it, so minus ad. And because we know that a in the y direction will be in this direction, this ay is simply the y component of ad. And therefore, we can say that ay is equal to minus ad times the sine of this angle alpha, using this angle right here. And so at this point, we have connected ay with the acceleration that we actually want, ad. So let's now use the same reasoning to also rewrite ty and f of gy, the y components of the forces that we're dealing with, in function of this angle alpha and also of the sine of alpha. Using some trigonometry, we see that if we project this t onto the y-axis, we get ty, and therefore ty is equal to the sine of alpha multiplied by t. The same can be done for this force of gravity. If we project it onto the y-axis, we get, of course, the y component. And therefore, the y component is equal to minus the sine of alpha multiplied with fg of 1. And on the other side of the equality sign, we simply have m1 now multiplied with minus ad multiplied with the sine of alpha. And at this point, we see that we can cancel out all of these sines of alpha on both sides of the equality sign. Therefore, we get the following equation: t minus the force of gravity on our first object with mass m1, is equal to its mass m1 multiplied by minus ad, the acceleration in the downwards direction. And this is actually the second equation that we need. And if you look at it, it's actually quite straightforward, and we could have obtained it much more easily. If we go back to our original sketch, then we see that this equation indeed describes this system right here, irregardless of our choice of coordinate axis, because we see that the acceleration of this object is equal to the sum of the tension and the force of gravity. It's because they all point in a similar direction, either upwards or downwards, that we can write the equation as we've written without any notion of this angle alpha. It simply drops on both sides of the equality sign. So to recapitulate, we now have two equations obtained from Newton's second law applied to the x direction for object 2 and the y direction for object 1. And the two equations are the following. For our first object, which is at rest on the inclined plane, we have that t minus the force of gravity of the second block multiplied with the cosine of the angle of our inclined plane is equal to the mass of the second object multiplied by the acceleration in the x direction. For our suspended object, object m1, we found that t minus fg of the first object is equal to m1, so the mass of this object, multiplied with minus AD. And AD is of course the acceleration in the downwards direction, which is the quantity that we want to find. And these two equations have to hold simultaneously. However, we see that we still have two accelerations in these two equations. We have AX and we have AD. Let's go back to our original sketch to see which accelerations these actually are. We have the acceleration AX, which is the acceleration in the x direction of the block on the inclined plane. And we have of course AD, which is the acceleration in the downwards direction. Now at this point we use the fact that this rope right here is rigid, which means that it does not change length. Therefore there is a constraint between these two accelerations. We know that the acceleration of this block in the x direction will have to be equal to the acceleration in the downwards direction. Because if these two were not equal, that means that these two blocks would move at a different rate. And if they would move at a different rate, then the piece of string connecting them would change its length. And therefore, we know that the magnitude of AX will have to be equal to the magnitude of AD, which is a relationship that we can now use to simplify these equations. So let me just rewrite it here. So AX is equal to AD. And this is simply the case because the rope is rigid, so it doesn't change its length. So if I call this equation equation 1 and this equation equation 2, then we can rewrite equation 1. We have T minus the force of gravity, but the force of gravity for an object of mass m2 is simply equal to g multiplied by m2, with g being the gravitational constant. And this of course has to be multiplied by the cosine of alpha, and this is equal to m2 now multiplied with AD, since we found that AX and AD will have to be equal. Or we can rewrite this equation to find an expression for the tension in the rope. If we just move the gravitational term to the other side of the equality sign, then we get the following, that T is equal to g times m2 multiplied by the cosine of alpha plus the mass m2 multiplied by AD. And this expression for the tension inside of the rope can be easily and intuitively understood as being a result of the force by which it is pulled on from both sides. Let's say that we again have our objects right here, which are connected by a pulley and a rigid rope. Now this rope is of course pulled on from both sides. From this side it is pulled on by this magnitude, and from this side it is pulled on by this magnitude. And thereby, by simply adding them up, we have the total tension in the rope. So let us now use this expression for T and fill it in our second equation right here. So what we then get is the following. First we have the tension. However, we now rewrite the tension as the sum of these two terms right here. So we have g times m2 multiplied with the cosine of alpha plus m2 multiplied with AD, the acceleration that we need. Then we have still this term right here, which is the force of gravity that is acting on the object with mass m2. Therefore, this will simply be g multiplied by m2, which is the gravitational pull on an object with mass m2. And this is equal to minus m1 multiplied by AD. And at this point, we see that we're practically done, because what we have here is an equation where AD appears, the acceleration in the downward direction of the second object. And all of the other terms in the equation are terms that we can easily fill in. We have this gravitational constant, which is simply 9.81 meters per second squared. We have the masses m1 and m2, which can also be easily filled in. And we have this angle alpha right here. and which we intuitively reasoned that this angle alpha will determine the acceleration in the downwards direction. And therefore we can simply rewrite this equation as a function of AD. We have AD multiplied by m1 plus m2, which is equal to g multiplied by m1 minus m2 times the cosine of alpha. And we can now even further rewrite this to get our final result. We have that AD, the acceleration of the second object in the downwards direction, is equal to g multiplied by m1 minus m2 times the cosine of alpha divided by m1 plus m2. And this is indeed the final result of our quite elaborate exercise. And now comes the most beautiful part about physics, because we've now did a lot of mathematical calculations, but this result can be checked with our intuition in different scenarios. Let me first briefly resketch the situation that we had. So we had a system where an object was on an inclined plane, and this object is connected through a pulley with an object that is hanging down. And now what we calculated is AD, the acceleration of the second object going in the downwards direction. This object has mass m1 and this object had mass m2, and this is our angle alpha. So let's look at the first scenario, where of course alpha is equal to 0 degrees. Well, let us calculate. Then we have AD is equal to g multiplied by m1 minus m2 times the cosine of 0 degrees is simply 1. And we divide this by m1 plus m2. And from this equation, we clearly see that if m1 is equal to m2, meaning both masses are the same, then we have that AD is equal to 0, so no acceleration. But what situation does this resemble? Well, if this angle alpha goes to 0, then we simply have the following situation, where the two masses are hanging by a single pulley. And therefore, if the two masses are the same, then there will be no acceleration because they will balance each other out. We see, however, if mass 1 is larger than mass 2, then this acceleration will be positive, and therefore mass 1 will actually be moving downwards. We see, of course, that if mass 2 is larger than mass 1, then this will be a negative number, and therefore mass 1 will be moving upward. So this is in complete correspondence to our intuition. Let's say that alpha is equal to 90 degrees, which corresponds to the fact where we don't have an inclined plane anymore, but simply two masses that are connected by a single pulley. In this case, we have AD is equal to g multiplied by m1 divided by m1 plus m2. And we see that in this case, AD will always be larger than 0, meaning that this mass will always be going downward. And this is also in correspondence to our intuition. No matter how heavy this mass is, it will always be sliding downward since we're not dealing with any friction. And as a last case, let's look at where alpha is equal to 180 degrees. Now this might be more difficult to interpret, but that would simply mean if this angle even rises much more and more until we basically have a vertical wall with the first mass right here connected via a pulley to the second mass right here, and both are connected by a single string. Now, of course, we see that at this point, both masses will just fall straight towards the ground. So let's see how this translates in our formula. We have AD is equal to, and again, AD is the acceleration of this mass right here, to g multiplied by m1 plus m2, since the cosine of 180 degrees is minus 1, divided by m1 plus m2, which is simply equal to g. So the acceleration of this mass right here will simply be the gravitational acceleration. Therefore, we see that our object will be in free fall, and this is exactly what we would think it would do, since this object right here is not pulling anymore by this string on this object. It's simply falling together with the object right down to the ground. And this brings us to the end of this quite lengthy video. But I hope that you're now more familiar with the basic concepts of how pulleys work. If you have any questions, leave a comment in the comment section below. If you enjoyed this video, consider giving it a thumbs up. And if you want to get notified by future releases, consider subscribing. And with that, I thank you for watching, and I will see you in the next one. Bye.